Welcome to this fifth video in this series where we're going to be speaking about gas loss. Okay, there are three principles I would like to touch base on. Okay, the first one is Avogadro's law. Avogadro's law states that equal volumes of all gases at the same temperature and pressure will have the same number of molecules. What this means is 1 mole of any gas equals same volume if and only if temperature and pressure are constant. Okay, so this is something very important. Okay, we won't be working any questions related to this, but you will have a couple of questions in your worksheet. Okay, so if you do have any problems, please feel free to ask. Okay, but this is something very, very, very important. Then we're going to speak about Dalton's law. Dalton's law states that in a mixture of non-reacting gases, the total pressure exerted is equal to the sum of the partial pressures of the individual gases. Okay, so if you have a closed container, the pressure of the container is going to be the summation, the addition of all the pressures of the individual gases in that container. Okay, and therefore we're required to find what a partial pressure is. So, in a mixture of gases, each constituent gas has a partial pressure, which is the notional pressure of that constituent gas if it alone occupied the entire volume of the original mixture at the same temperature. So, let's say we have air. Air is equal to 78% nitrogen and let's approximate 22% oxygen. Okay, so the percentage of the other gases, we put them all into oxygen. Okay, now air, the pressure of air is equal to 1 atmosphere. Now, to find the partial pressure of these components, so partial pressure is going to be equal to the mole fraction times total pressure, where the mole fraction is equal to moles over total moles. So in this case, we can work out the partial pressure for nitrogen and the partial pressure for oxygen. So partial pressure nitrogen is equal to 78 over 100 times 1, which is equal to 0.78 atmospheres. Whereas the partial pressure for oxygen is equal to 22 over 100 times 1, which is equal to 0.22 atmospheres. It is very important that when we add the partial pressures together, they are going to amount to the total pressure. Okay, and in fact, if we add 0.78 plus 0.22, it's going to be equal to 1 atmosphere. Okay, so the partial pressures, all they're saying is what they're constituting from the total pressure. Okay, so let's work a couple of examples on partial pressure. A container holds 3 gases, oxygen, carbon dioxide, and helium. The partial pressure of the 3 individual gases is 2 atmospheres, 3 atmospheres, and 4 atmospheres respectively. So what is the total pressure inside the container? So here it's going to be relatively simple. Total pressure is equal to partial pressure O2 plus partial pressure CO2 plus partial pressure HE, which is going to be equal to 2 plus 3 plus 4, which is equal to 9 atmospheres. So the total pressure here is going to be equal to 9 atmospheres. Okay? So, second example, a mixture of 2 moles hydrogen, 3 moles ammonia, 4 moles carbon dioxide, 5 moles N2 exert a total pressure of 800 kilopascals. What is the partial pressure of each gas? So here, what you would have to do is work them out individually. Partial pressure H2 is equal to moles of H2, 2 over the total number of moles, which is 14, times the total pressure, which is 800, which would be equivalent to 114.3 kilopascals. Okay? The partial pressure of NH3, we're going to be doing the same. Moles of NH3 over total moles times total pressure, which is going to be equivalent to 171.4 kilopascals. Okay, partial pressure of CO2 is going to be equal to 4 over 14 times 800, which is going to be equivalent to 228.6 kilopascals, and the partial pressure of N2 is going to be equal to 5 over 14 times 800, which is equal to 285.7 kilopascals. Okay, if you were to add all the partial pressures together, you would realize that the total will be 800 kilopascals. And in fact, if you want to double check your work in an exam or when you're studying, you can add everything up and you would know what you've got, whether it's correct or not, simply because it should add up to 800 kilopascals. And in this case, if we were to add them up, it would in fact add up to 800 kilopascals. The combined gas law. So there are 3 gas laws, individual gas laws, and in chemistry we normally speak about the combined gas law. And this is PV equals nRT. And this is the gas law, we call it the ideal combined gas law or the ideal gas law, or okay? And it's ideal because we assume that gases are ideal systems, okay? Now, PV equals nRT, where P is equal to the absolute pressure of the ideal gas, V is the volume, N is the amount of gas, T is the temperature, and R is the gas constant. Whenever we're doing something like this, we need to know what the units are going to be. So pressure is going to be in Pascal. Okay, pressure is going to be in Pascal, volume in meters cubed, temperature in Kelvin. N is the amount of gas, so this will be in moles. In fact, I highly recommend that anytime you do this, you write PV equals nRT on the left of the paper, and on the right, you write PV, N, and T, and you would be able to write the proper units there and make sure that the conversions are all correct. So, an elemental gas, meaning that it is made up of only one element, has a mass of 10.3 grams. It occupies 58.4 liters at 1 atmosphere and 2.5 degrees Celsius. Identify the gas. So, we're going to be using PV equals nRT, and as I advised, I would highly recommend that to decide we write P, V, N, and T. R is a constant, so there's no real need to write it. So pressure is going to be 1 atmosphere, which we know is going to be equal to 101.325 pascals. So if you don't know this conversion, you should know it, or you should learn it, okay? So 1 atmosphere is equal to 101.225 pascals. I don't believe it's given in papers. So I do believe that you should know the conversion beforehand. Okay, volume is 58.4 liters or decimeters cubed. So to change them to meters cubed, we need to divide by 1,000. Okay, N in this case, we do not know, and T is 2.5 degrees Celsius, which is equal to 275.5 Kelvin. Remember, changing from degrees Celsius to Kelvin, it is plus 273, okay? And then you can put everything in your equation. Personally, before I put everything in the equation, I would rather make N the subject of the formula. I find this to be a lot easier. And at this point, then, I can put in the numbers. Okay? And once I put in the numbers, then I can find what the number of moles is going to be. Okay? And the number of moles in this case is going to be 2.58 moles. The question is, identify the gas. Okay? The question is to identify the gas. And in order to be able to identify the gas, what we would need to do, okay, what we would need to do is to first start by finding the mass of 1 mole of this gas, okay? So we would need to find the mass of 1 mole of this gas. So 2.58 moles is equal to 10.3 grams. 1 mole is equal to how much? And this would be 10.3 divided by 2.58, which is equivalent to 4 grams. Okay? Which is equivalent to 4 grams. Okay? Therefore, it would be helium. So this gas would be helium. Now, do I expect you to know the masses by heart? No. But most of the time, if you have a question like this, you will have the periodic table alongside with you. Okay? The last question we're going to be working for empirical formula, for gas laws is going to be example number 4. And this is going to be a gas has a temperature of 300 Kelvin and the pressure of 104 kilopascals. Find the volume occupied by 1.05 moles of this gas, assuming it is ideal. Now that assuming it is ideal is very important. So PV equals nRT, where we have pressure, volume, moles, and temperature. The pressure is 104 kilopascals, which is going to be equal to 104,000 pascals. The volume, you don't know, okay? Moles equals 1.05 moles, and the temperature is equal to 300 Kelvin. So at this point, as I told you beforehand, I would prefer to put the subject of the formula so that I would be able to just put in the numbers and see what happens. And once I do that, okay, 1.05 times 8.314 times 300 all over 104,000 pascals, I will get a number of 0.0252 meters cubed, okay? And that is your answer for this particular question. You have a few questions in the worksheet in the description of this video, so feel free to work those out, and again, if you have any queries, do not hesitate to ask me. Okay, thank you, and I will see you for video number 6.